Yeah. Okay. It's now being recorded. Okay, see. Right. So we're doing a kind of review of what we did last time and taking some questions from linear algebra. So how to identify independent columns? Well, literally speaking, what we can do is just, this is a kind of pseudocode. You can take the first column and put it in C, okay? And C will summarize all linearly independent columns in that case. You can take the second column. If it is a multiple of the column 1, you don't put it in C, otherwise you can put it in C. You can take the column 3 here in that case, and if it is a combination of columns 1 and 2, you'll have to find the combination. If it's not a combination, then you can insert it in C. Okay? And you can proceed till you go through all the columns. And in that case, the number of columns in C would be equal to R. R here is the rank of a matrix. Okay? And they will form what you call a basis. Can you remind us, guys, do anyone remembers what is a basis of a vector space or a column space in that case? Do you guys remember this from linear algebra? What is a basis? Yes, Abdullah.
It's the minimum number of columns to generate all columns.
Yes, in other words, it's a minimum number of columns, or in other words, of vectors to generate the whole space. Yes. The left outcomes are combinations of those basic counts in C. So for this case, for example, I'm taking the matrix A, where we have column 1, which is all in ones, and column 2 is just 3 times column 1, column 3 is 8 times column 1. And you can see, since we can only have one independent column here, we've taken it, we can form this kind of factorization where 1, 1 multiplied by 1 to 8 can generate back our whole matrix. Got it? And the second case, where we have 2 linearly independent columns 1 and column 2, and column 3 was the sum of column 1 and column 2. You can check it. 2 plus 1 equals 3, 3 plus 1 equals 4, 5 plus 7 equals 12. We did the same thing. We applied the pseudocode, or kind of the algorithm we defined in the previous slide. And if you multiply this matrix C, we obtain it 2, 3, 5, 1, 1, 7 by 1, 0, 1, 0, 1, 1. You can obtain A back. As you one can question here, how are we able to obtain R? How are we able to obtain R? Well, it's quite easy, because if you are doing a column by row operation, well, you need to do what? You need to regenerate the first column. That's why I'm multiplying by 1, 0. And if you want to generate the second column, that's why you multiply by 0, 1. And finally, the last column should be the sum of the columns 1 and 2. And that's what we are doing. That's why we're doing 1 plus. So in general, in algebra, you know, guys, that the row rank, or the number of linear independent rows, is equal to the number of linear independent columns. And this is true for all matrices. What we talked about also is the regular way to perform the product, or what we call the dot product of matrices. So just to remind you, if you have 2 matrices here, A and B, and they give a matrix C, okay? For example, if I'm taking the second row of A multiplied by the second column of B, they do give me what? They do give me this element, the element on the intersection, which would be 2. This should have been the third column. What should it give me? Give me C2, 3. Am I right? Why CT2? So there is a typo here, right? Okay, so let's go back to the fundamentals. Can I only multiply square matrices by each other?
Yes, you can. Square matrices.
Yes, I know I can multiply square of matrices, but there is one single condition to perform a dot product, right? What it is?
The number of columns in the first matrix is equal to the number of rows in the second matrix.
Yes, Khalid is talking?
Yes.
Thank you, Khalid. So the condition is that the number of columns in the first matrix equals the number of rows in the second matrix, right? So here, for example, if you have 3 by 3 multiplied by 3 by 3, so there is no problem with that. Okay, so if I multiply the second row by the second column, I should obtain the element which is placed here and not on C23. It should be here, right? I should apply C22. So there is a typo here. It's misleading. Should have been C22. Okay. But there is another way to perform this product, which is to perform what you call columns of A times the row of B. Okay. So for example, if I'm talking about this, these two vectors U and V transpose, if I multiply them by each other, 2 to 1 by 3, 4, 6, I obtain this matrix: 6, 6, 3, 8, 8, 4, 12, 12, 6. And intuitively, one might wonder why is that happening? How come a single-lined column multiplied by a single-lined row gives us a 3 by 3? Intuitively, it might appear weird, right? So, well, just remember what Khalid said. We have here what? A 3 by 1, صح? Multiplied by 1 by 3. Okay? And what we should obtain if you do the dot product, the matrix we obtain should be 3 by 3. Why? It takes the number of rows from the first matrix and the number of columns from the second matrix, right?
Yes, yes.
Am I right? Okay. So, so one can think here about the way to use this, because, in fact, you were able to say that if I store two vectors, 2 to 1, 3, 4, 6, and I can obtain a 3 by 3 matrix. Huh? How many numbers do we have in the two vectors U and V? 6. Huh? 6 entries. 3 plus 3 entries. Well, if I have 6 entries, I'm pretty sure it takes less memory than 9 entries. Okay? You agree with this? So I'm pretty sure that I can do just, if I know the kind of operators I can apply to regenerate back my data, I will do that if I would like to save space in my memory. Am I right? What do I need to store? What do I need to store in my memory? I need to store just the two vectors U and V and the kind of operators or the operation I'm going to perform to generate any matrix. Am I right? I repeat, if this matrix, for example, I obtain here is too large for my memory, okay? Aisha, or am I going too fast? Yes. Maybe I'm not making myself clear. Okay. If my memory, for example, supports only 8 elements, okay, let's suppose it supports only 8 elements. Can I still store this matrix?
No. No.
Because I'm just showing you how to do it. I'm pretending that if my memory had only 8 elements, I can still store this. Yes, Abdullah.
You can save it in the first form, which is the 221 times 346.
Yeah, I can say, well, in fact, what I just said is that I can still record the two vectors. This one takes 3 units, the other one takes 3 units. And what I can do is just store the operator, saying I'm performing a dot product and I'm done. Okay? So this way I can regenerate my data in a way that preserves my memory. I'm not really looking too much memory, or I'm not using my whole memory. In fact, I left from 8, I left one piece which was empty. You got it? And hopefully you understand that this is the whole intuition behind this kind of factorization, is that usually data, when it comes in a huge form. You get it, guys? So mathematically, how to deal with this? How to deal with this is to perform a kind of factorization on this data. Okay, kind of compress it in this kind of form, for example, in this case, because, well, this matrix is a one-dimensional or one-ranked matrix, and I can just store these two vectors, u and v. And I know, I said to myself, well, I know how to really generate it if I need. You got it, guys?
Yes.
Okay. So this is an idea that will follow us, inshallah, all through the course. That the reason we are perform these kind of, this is a very simple factorization. We'll see just in a couple of minutes, more complicated one. And this is the whole idea behind taking a linear algebra part in data science. You got it? So the whole idea is how to treat huge data. So by definition, we said earlier that by definition, the row space of any matrix A is the space of the transpose matrix. So for example, if you take UVT transpose, so you transpose it again, you should be able to, by, this is a property from linear algebra, UVT transpose, what happens, the T, when it gets inside, it inverts the product. Okay? So UVT all transposed gives you VUT transpose, which is also could also be obtained by 1 by 1. I mean 3, 4, 6, yani 3 by 1 multiplied by 1 by 3. Okay. So basically what is just saying, if you are able to store this matrix in using two simple vectors, well, you can store this, it's transposed the same way. Okay? Right. Let's move forward. The same way, so for example, if I'll move just backwards, guys, if you allow me. So basically, what I can do, for example, for this matrix, I'm pointing to this matrix, which was, what was the rank of this matrix, guys? The one I'm aligning here?
2.
2. Okay. So, so what I'm saying to myself, I can just store these two vectors instead of the 3 vectors, right? Or the 3 columns, the 2 columns instead of storing the 3 vectors, the 3 columns. I can store, I repeat, I can store the 2 columns instead of storing the 3 columns. Well, I have a question for you. What is the you it before in linear algebra? How can we obtain this R? You've seen it before, yeah, listen. This is what we call the reduced row echelon matrix, right? Yes. I'm pretty sure you've heard this before, huh? Yes. And most probably in mathematics, and more specifically in linear algebra course, not on Netflix or someone else. Okay? So this is a reduced row echelon matrix, which comes from where? Which comes from A. صح? And the usual way to note it is RREF. RREF, reduced row echelon. Okay. So let me go back to my things. I've talked last time also about another way to simplify the information we had in the matrix. And so not only we were able to get a 3 by 3 matrix by multiplying 3 by 1 and 1 by 3 vectors, but we can also obtain a more complicated product like this one, A times B, where A, as you see, is m by n, so not forced to be square, and B is m by p, okay? And what we just said is that one can write this product at the sum of 1 by 1 or ranked 1 matrices. This is what we said. Okay? Question. How many multiplication do we have to perform if I'm doing an A by B or A dot B? Well, if you are performing this multiplication, well, I'm just writing it here. It's MNP multiplication, or for those who are not familiar with complexity, even the guys in system engineering, I see they have to deal sometimes in algorithms with complexity. So why are we doing MNP multiplication? Because if you remember, if you're doing a row by column dot product, what happens? You have how many columns here? Okay. In every, yeah, go ahead, Chaka. Anyone wants to talk? So think about A as having how many columns? We said n columns. N columns, okay, multiplying n rows. So for a single column by row, how many multiplication you do? Or let me talk about it in a reverse. If you do a row by column, in every row, how many entries you have? You have n, huh? Yeah, multiplying n. Yeah. Right. So you have m rows. Okay. And what are you doing? You are doing it n times. Okay. On the columns of B. So that's why you will end up, whether you do it column by row or row by column, you will obtain MNP multiplication. So if I go back to my example here, AB, I have one way to do it, so just simple 2 by 2 here. 1031 multiplied by 2405. Okay, so I'm doing just the column by row multiplication. So, or just the, I'm summarizing it. It's 13 times 24 plus 01 times 05. And you can actually check, well, this is not the regular way to do it, right? Correct me if I'm wrong. If you've seen it before this way, I'm sorry. But the regular way to do it, yeah, the way to do it, I'm writing on my slide, okay, is to do what? Is to do 1 times 2 plus 0 times 0,
yes.
so?
Yes.
So, yeah, then 1 times 1 plus times 4 plus 0 times 5, all right?
Yes, 4.
So 3 by 2 then plus 1 times 0, so it's 6. And then 3 by 4 plus 1 times 5, so you get 17. Okay?
Yes.
But here, this is another way to do it, is to do what we call the outer product, which happens to be just the sum of the column by row multiplications. You go, so I'm checking out. I'm checking that this works. So it's the first row is 1, 3 multiplied by the first row, 2, 4, plus
yes.
0, 1, second column by the second by the second row. Okay? So I'm doing each element by itself. This is we have here a 2 by 1 multiplied by 1 by 2, which gives me 2, 4, 6, 12. Am I right?
Yeah.
And 0, 1 times 0, 5 gives me 0, 0, 0, 5. Now, if I sum it up, I get the same answer I had before I was expecting. Got it? Well, this doesn't save time in terms of a number of multiplications performed, but this is another way to see things. Okay? So the dot product, whether you do a row by column operations, or here column by rows, the sum of the column by rows, it gives you the same thing. Yes? Any questions?
Applicable for only square matrices or
Here? No, not only for square matrix.
okay.
Okay? the fun to try it also with other matrices. So what we said last time is that data science, in generally, we are looking for the most important part of a given matrix. So that's why, if you remember last time, I said that if you are working on a huge data, better refine it before. Refine it in terms of determine whether there is any noise in it, whether there are errors, mistakes, before applying your treatment or before trying to study what are the patterns. Okay, and the most important thing, try to also not to store everything. That store the things that are variables that are very important for our work. So we don't want to store the biggest part of A. We want to store the largest piece of A that can generate the whole matrix. So in our previous case, we had one by one, two U and V. For this 9 by 9 items matrix, I mean 3 by 3, we were able to store the two vectors U and V. Okay. So in our case, in the case AB here, these two matrices we had here, I mean 2, 4, 6, 12, and 0, 0, 0, 5 are rank 1 matrices. Do you agree with this? Well, they are rank 1 because what we have here, you have 2, 6, 4, 12. Well, here you see we have one linear, in fact, one column is enough, and also one column here is enough because you have just the 5, which is a non-zero. Okay? Remember, the zero matrix is by itself a zero rank matrix. So if you have only one single entry here, you have a rank 1. So we'll talk now about factoring, and we'll see some important ones. Now, this is the things we didn't see before. Factoring, so which is a dominant theme in applied linear algebra. And we'll see many ways how to factor. And I think I convinced you, or I tried at least my best to convince you that there are some opportunities or some gain, some payoffs, some advantages of factorizing matrices, like factorizing it in this very simple form CR, and look for the pieces or the chunks of A. So factoring, for example, A into CR is quite simple because you just need to identify the independent columns. And R, as we said before, is just the row echelon, reduced row echelon matrix you can obtain from A. Factoring itself takes longer, especially if the pieces involve eigenvalues and singular values. We'll see later what are singular values. But let me focus on the most important things we have for today. What are eigenvalues, guys? Do you remember what is an eigenvalue of a matrix? Don't rush. Too many people are raising their hands. I'm being sarcastic. Okay, how do you obtain the... Yes. Don't hesitate. Go ahead. Is it Abdullah? So how do we obtain the eigenvalues? Do you guys remember? So to obtain the go ahead. Determinant of A minus lambda I should be equal to 0. So you're looking for the lambda side. Okay. What is I here? The identity matrix. Okay, and you should have A determinant of A minus lambda I equals 0, and these will give me the eigenvalues. Type. What about the eigenvectors? You guys recall what are the eigenvectors? Okay, it's not too bad, guys. It's already enough. So in the next part, I'll talk about one important factorization among these 5. So first of all, what we'll talk in this course in general about 5 important factorization. The first one, I think we've seen it before. It's the LU factorization, or what we call the LU elimination. We'll talk about the factorization QR. We'll talk about the factorization where S is a symmetric matrix, and you can write it as Q times lambda. This is lambda in Greek, lambda capital. Q lambda QT, or in the most general case where A is not symmetric, you can write it as X lambda X minus 1, X inverse. Or this factorization where U is equal to V sigma capital V transpose. So let's talk about the preferred one to the other, which is this one, this kind of factorization. So before, I'll just talk briefly about each kind of factorization. So the LU elimination, which we commonly call the LU elimination, is to find combinations of rows that take A to U and U back to A. The matrix A is lower triangular. Okay, so there is a gain here in terms of space if you are storing a lower triangular and an upper triangle matrix. Okay, lower triangular means that everything above the diagonal is 0, and an upper triangular, everything below the diagonal is 0. And the second kind of factorization, where you write A equals to QR, it comes in fact from the orthogonalization of the columns A1 to An. What do you mean by orthogonalization? It means making the columns, their scalar product should become equal to how much if they are orthogonal? 0. Okay, two vectors are orthogonal in space, their scalar product is equal to 0. You guys remember, for example, if I'm multiplying in the Cartesian plane 1, 0 by 0 line, I get a 0. They are orthogonal. And Q has here orthonormal columns. So QT times Q is equal to I. So in fact, the transpose of Q is the identity matrix, and R is upper triangle. So the preferred one here, what we will talk about is this one, the one where a symmetric matrix S could be written as Q times lambda QT. And in fact, the eigenvalues are placed on the diagonal of the lambda matrix, okay? And the eigenvectors are placed in the columns of Q, and then, of course, in the rows of Qt. Okay. So before moving forward, so this is just adds a little bit of things. So let me detail what we are talking about here. So S is symmetric matrix, so that S equal to ST. Hopefully you agree with this. This is the definition of symmetric matrix. It has orthogonal unit eigenvectors. Okay. What is an eigenvector? You guys recall? Okay, eigenvector means that Q is an eigenvector if SQ is equal to lambda Q. So in other words, eigenvectors keep the same direction for S. Okay? So once you find the lambdas, you should be able to find all the Q's that make it work. So in fact, what does it mean? It means that you should end up with A minus lambda I times Q equal to what? Or S minus lambda I times Q equal to what? You guys remember how to find the eigenvectors? If I take this identity, this equation, I place here S. Should be able to find 0. Am I right? Because if you bring the lambda Q to the other side and you factorize from the right, so you need to introduce then to make the sizes equal lambda times I. Okay, so at the end you're seeking the Q's that make S minus lambda I times Q. This is the homogeneous linear system be solved. Okay, this is a way to find the eigenvectors. So these perpendicular eigenvectors, the columns of Q, So you basically get Qt equals to Q inverse. And the lambda contains the real eigenvalues, and you can verify in that case that you have the what was expected. You have this definition is that S is equal to Q lambda Qt. Okay, this is specifically detailed in the Python code I'm providing. Okay. So before moving to this Python code, which I will share with you, I would like to solve one simple problem from the problem set, if you agree. So I still have 10 minutes left. So, for example, if I take this, this is problem 5 from the problem set 2. Well, it's just a practice, guys, and just to make you feel more comfortable. This is not a theoretical mathematics course. Hopefully, you understand this. Are you cheering up? Happy? Yes. I'm pretty sure. So the main goal is to see the links between mathematics and formally saying data science. So here in this problem, we're trying to check that the associativity law from dot product of matrices and how performing the operations on columns is the same product as if performing column operations. So basically, you have three matrices, A, B, C, and we're checking that A, B, all times C is equal to A times BC. Okay, so I uploaded already one file. Okay, and I'm trying to I'm trying to share now with you the screen of application. Okay, hopefully it's going to work. Okay. Okay, are you able to see my my application right now?
Yes.
Okay, so this is just Visual Studio. Guys, Visual Studio is a programming platform which is quite famous, supported by Windows. In fact, it's released by released by Microsoft for at least more than 20 years right now, and it supports programming in many languages, including C, C++, Python, Visual Basic, and stuff like this. So basically, I'll be working during the whole summer with you on Visual Studio most of the time, except when I'll be using R or Math. Okay, so here I prepared for you a file called 15.py, and which I shared with you on the Blackboard already. I already uploaded it. So what does it do here? I'm just trying to check the associativity law performing with some code in Python. So first of all, I'll go through the sentences. The syntax are supported by Python. Well, Visual Studio, guys, you can download it now for free. It's marvelous. It works very well on Windows. So you can upload it. You can download it for free, and you can upload the mathematical libraries that will be called. So, for example, the first syntax here, what it does, it imports in NumPy. NumPy, which is a very important numerical package in Python. Okay, so when I say import NumPy, so it's gonna import it. So if you don't have it, of course, already, you can just here go in this environment. Okay, check Python environments, and you just look for it, NumPy, and you just run the command to install it. And it's quite easy to do. If it doesn't work, just 1 minute, look on Google, it's gonna work. Then I'm gonna just look for the NumPy package. I'm gonna just use the linear algebra package and the inversion, for example, if I'm so for example, in this file, the one example 5, I have the three matrices A, B, C. So I gave input to matrix A, B, and C. So for example, here the way to define a matrix to use arrays. So on this row, what I'm saying is that NP, so I'm calling the NumPy package, define me an array which takes 1A and 0, 1. You got it, guys? Everything clear? So what A it carries, then it carries 1A, 0, 1. It carries 2 rows and 2 columns. And for me, A was just initialized to 2. And I'm saying to NP, I'm saying NumPy, define me matrix B, also define me matrix B. And B takes B1, B2, B3, B4. And C takes 1, 0, C1. Okay? So I'll be just perform the 2 products, the 2 dot products, A times B first. So to perform the dot product, I just need to call NumPy, okay, perform the dot product between A and B. You see? Perform the dot product between A and B. I'm sorry for this window which appears and goes on. So, so this command, what it does, it performs the dot product A times B, and I print it out. Print AB. So what comes between the two is the 2 commas or 2 apostrophes is just what the message you want to display. Okay, and it will display you AB. And then I'm saying also ABC. I'm calling a new matrix called ABC, with the result of the dot product of AB by C. And I'm asking my computer or my program to display it also, to print it out. Similarly, I'm defining a new matrix called BC, which is the dot product of B and C. I'll display it, and I'll display the alternative way to find the dot product, which is just to A times all of B times C. So if I run it out here, I'll be trying to run it. So I'll compile with you, so you see it live. So this is what should happen. Okay, what should happen? Well, it takes a couple of seconds to load because it's going to compile, and it's going to display the matrices you entered, which you computed. Sorry, you have AB 11, 1, 4, 1. So ABC is 9, 1, 2, 1, and you also asked it to display BC, which is B times C, 5 minus 1 to 1. And can you check that A times C is also equal to AB all times. So you get 9, 1, 2, 1. Got it? Any question on that, Shabbat?
No.
No.
Okay. Right. So I also, what I did also, I prepared another file, which is the spectral file. I uploaded on the Blackboard, which verifies the conditions that were mentioned in the slides, where if you have S as a symmetric matrix and you generate the eigenvalues and the eigenvectors, then you should be able to verify that S is equal to Q times lambda times Q transpose. So I wrote a piece of code here, okay? And here I'm defining, for example, S as the matrix which takes 1, 1, 0, 1, 0, 1, 1, 1. And you can check already that this is symmetric. And I'll be calling the 8th function in the linear algebra package to upload in the 2 vectors W and V. W is going to take the eigenvalues, and V is going to take the eigenvectors. So I'm commenting here. What you see in V are the comments I added to my code. So you can also display the eigenvalues and the eigenvectors if you wish. And I'll be performing a couple of linear algebra operations. So I'll be transposing V. So V, remember, carries here the eigenvectors. I'll be transposing it. And what does the mathematics says? It says that in that case, if S is symmetric, then the eigenvector Qt is equal to Q inverse. So I'll be computing the transpose and the inverse of V. This is what I'm actually doing here. And this gets you to familiarize with these kind of things we're using in Python, okay, following the NumPy package. I'll be displaying them here, and you'll have the time to go through the code, inshallah. And I'll do the difference if you want, just a simple operation to verify that this is really exactly the same. I'll perform the dot product between V and V transpose to check also again that V transpose is equal to V inverse. I'll generate the matrix lambda, which takes lambdas, the eigenvalues in the diagonal. So I'll be multiplying it by the identity matrix. And this line I'm pointing on this line where lambda capital equals W times this array. And I'll print out the whole element, and then I will check that in fact I should perform Q times lambda times T gives me also my S. So this is running, and this is the piece of code that verifies the mathematical properties we verified, we talked about. So this is the printout of my code. I'll have my sum matrix S 1101011. I obtain it here as I'm saying I'm displaying the eigenvalues minus 112. So on purpose I took a case where I have integer values. The eigenvectors, I obtain the transpose, the V inverse, and I perform here the difference between the transpose and inverse. I check that this is not exactly 0, but this is very, very, very close to the base. In fact, this number to the power times 10 to the power minus 16. Okay, so this is exactly 0. I'll do the operation as the V transpose to verify that it gives me the identity. Okay, I'll obtain the big lambda, the capital lambda matrix, and I perform the operation where I do the operation Q times lambda times Q inverse, and this matrix R I'm pointing to, I obtain R almost exactly equal to S. So mathematically this works. So you see this is exactly the same as a matrix S. So this is in fact the lecture for today. So I'll stop sharing this. I'll go back to my file. So this is detailed also, explained on the last slide of the lecture notes. And hopefully you enjoyed it, guys. Hopefully it's clear. Inshallah, we'll see each other on Thursday. We'll talk more about this, inshallah. And this is the last slide I was talking about that summarizes everything. And if you have any question, please go ahead or leave it for next time. Yes, Hussein, Abdurrahman.
Yeah, Doctor, do we have to program and learn how to program?
You do. Yes, you do. And we go smoothly together with this. If you are planning to do data science, you will know you need to know how to do programming.
And which language will we use? Python or C++? Or?
We'll do it in Python. We'll try also to do it on MATLAB and R. And this is a minimum required in data science.
Okay.
Okay. Anything else, Shabab? So we'll go smoothly together, inshallah. Yes. Anyone else?
Are we required to download this program?
Well, it's available for you. Yes, go ahead. This is my code. I uploaded for you. Please do it. Anyone else?
And yeah, final thing. The recorded session, we can't see it because I think the session is hidden from Blackboard.
I'll check who's talking. Hussein?
Yes. Hussein Abdurrahman.
I'll try to check how to make it available, inshallah. Okay?
Okay, thank you.
Thank you very much, guys. Yes, please, go ahead.
Most of us actually don't have the essential background about Python and R and MATLAB. How we will deal with
Yes,
it?
this is the main purpose is to learn new things. Abdullah, right?
Abdulaziz, I know, but
this is the main purpose. That's why I definitely not that long ago I didn't know Python at all. Okay, I used to know only C, C++, so I started learning it. It's going to be very easy, Abdulaziz, I promise you.
Okay, thank you.
It's much easier than C++, believe me. So if you were able to learn C++, you won't have any problem. So I followed the code, I commented all the syntaxes, guys. I wish you you take a look at it and do what I told you. Just use your programming platform, whether you're on Windows or Mac or Linux, and it's gonna perform quite well. Okay, and I will help you with that, Sean. Okay, Shabab?
Okay.
Yeah. Don't worry, Shabab. Don't get. I hope I'm not threatening you. This is not a mathematics course. This is a data science course. So we'll do a little bit of math, a little bit of programming, and to treat data. And hopefully we'll enjoy. Yalla, assalamu alaikum. Assalamu alaikum. See you.